Hi, I'm Peter Rowlett.
And I'm Katie Steckles. And Peter, what's today's mathematical object?
So today's mathematical object is a UUID, which stands for Universally Unique Identifier. And annoyingly, they're also known as GUIDs, Globally Unique Identifier, depending on whether you prefer your identifiers to be global or universal.
Right.
So there is a problem that happens, that is that things need ID numbers, right? So I was making this thing at work, which I'll not bore with the details, but I needed to sort of have a system that would generate unique links for people. And there are lots of ways to do this, and I think what I did in the end was I just made a random thing and put it in a while loop so that if it wasn't actually unique, it just made another one until it was, which it shouldn't take too long to do because of the way that I set up this random number. But there are proper ways of doing this, and loads of things need ID numbers. So things have product numbers. I'm twice a week at the moment taking a COVID lateral flow test, and that has a little serial number on it that I have to type in when I report the number. File systems, databases need keys that are unique. There are loads of things that need unique numbers. So enter UUIDs. This is a 128-bit number, often expressed in hexadecimal. So it's not 128 characters, if you like, if you convert it to hex. But what's special about these is that there is no central registration authority, and there's no coordination between systems that are generating these numbers. So it's not like you go to someone and say, hello, I need a unique number, please, and they send you a unique number. It's you just generate one, right?
That's such a brilliant idea. It's a service you could provide, just artisanal integers for,
Yes. But anyway, that's quite surprising for a unique ID system, is that if I generate one and you generate one, so anyone can generate a UUID, it should be unique. So for example, I fired up Python and generated one, which is then in the episode title here, is what should be a unique UUID that I generated by typing in some Python code earlier. And so if I have a big database of data indexed by UUID, and so do you, we should be able to combine our two databases with no clashes. These things are supposed to be unique, even though we haven't collaborated on making them unique. And what this sort of caught my eye, this line on the Wikipedia article says, while the probability that a UUID will be duplicated is not zero, it is close enough to zero to be negligible.
Right.
And that's that sort of thing where you get mathematicians get a bit itchy about stuff where it's like, we've tested 10 million cases and it's fine, so let's just assume the theorem is proved, right? It's that sort of problem.
Yeah.
So I find that interesting. So I was sort of looking into this. They were originally used in the 1980s in Apollo Computer's network computing system, which was a distributed computing system. And then the thing is, there are lots of different versions of UUIDs. So, as I say, it's a 128-bit number. 6 or 7 of those bits tell you what type of UUID it is, because there are different types. So that leaves you with 121 or 122 bits to allocate, depending on which version you're dealing with, in a slight complication that doesn't really matter. Some of them are space-time based. So the way that they're defined in space is they use the 48-bit MAC address of the computer that generated the UUID. So every computer has or every device sort of has a MAC address. Your Wi-Fi aerial and your computer and your laptop or whatever will have a MAC address associated with it. So will your phone, so will your hub, and they all know how to talk to each other because they have this unique number. So that 48-bit MAC address is then combined with a 60-bit timestamp,
right,
which is the number of 100 nanosecond intervals since the Gregorian calendar was first adopted at midnight on the 15th of October 1582. Of course.
Yep.
Or at least that's when it was first adopted by a bunch of Catholic countries. It's actually not when it was first adopted in my country, for example, but that's when it was first used in anger, I think. And of course, why wouldn't you define time as the number of 100 nanosecond intervals since the Gregorian calendar was introduced? I mean,
yeah.
Time's arbitrary anyway, right? So the measurement of it. Then you add, because that might not be unique, because if you're generating these things pretty quickly, it might be that you generate 2 within the same 100 nanosecond interval.
Oh, of course.
So then it throws in another either 13 or 14-bit clock sequence, which just extends the time sequence, just in case the clock doesn't advance quickly enough. So it's supposed to be unique in space because it's unique to your MAC address, and also time, because you've got this within this 100 nanosecond interval, you've got another 13 or 14 digits going on there. So this does mean that you can use the UUID to find out which computer generated it.
Right, yeah.
Because you can reverse the MAC address from it. But you can use, the spec does allow you to use a random 48-bit ID number instead of the MAC address if there isn't one available, or you don't want to reveal it, or whatever. So that's the thing. And then you bundle that with the 6 or 7 bits to indicate the version, and that's your UUID. There are other versions which use different hashing algorithms on a namespace identifier. So the namespace identifier is itself a UUID that's supposed to represent a URL or something unique. Anyway, so there are these sorts of ones. And then finally, there's a version that just uses 121 or 122 randomly generated bits. And that's what I've done for the episode title. I've used UUID version 4, which is the one that's just random.
Okay. So that I can sort of see how it being generated by a particular computer at a particular time would make sure that they're all unique, because, unless you can travel back in time and use the same computer on a different day, you're not going to have the same details. Sorry, use the same computer on the same day at the same time. You're not going to be able to generate the same number again. But if you're allowed to just pick any MAC address, or if you're allowed to just generate random numbers, then surely the chances of a clash are non-zero.
Which is what it says, right? So yeah, absolutely. So that's my next thing to think about then is collisions, right? How often are these things going to generate the same number? And yeah, basically, if it's the same machine as you say, then you can't have two different machines generating the same number if they're using their own unique either MAC address or namespace identifier or whatever. So then you've got to worry about the random. For 122 bits, each bit can have one of two values, say 1 or 0. So there are 2 to the power of 122 possible 122-bit strings, which is about 5.3 times 10 to the 36 possible numbers that you can generate.
Yeah, so like a 36-digit number. I'm just trying to get Wolfram Alpha to tell me what it would be, and it offers me the full name that's 5 undecillion, 316 decillion, 911 nonillion, and so on. And underneath that, it also helpfully suggests 5 billion, 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 ...
Right. Very good.
Sensible. But it's like a 37-digit number, so
yeah,
like quite a lot.
So Wikipedia has this helpful contextual thing in the way that it sometimes does. It says, for example, the number of random version 4 UUIDs which need to be generated in order to have a 50% probability of at least one collision is 2.71 quintillion.
Right.
So if you generate 2.71 quintillion of these, you've got a 50% chance that there's one collision in there.
Yeah.
It says this number is equivalent to generating 1 billion UUIDs per second for about 85 years.
Okay.
And that a file containing that many UUIDs at 16 bytes per UUID would be about 45 exabytes. I looked up exabytes. An exabyte is 10 to the 18. And Wolfram Alpha says the information content of all words ever spoken is about 1 exabyte.
Right. So yeah, because I guess the thing is, you can say like, oh, there are loads and loads of these. Like with anything like this, you say, oh, there's so many different possible ones, and that is okay, provided you're not generating them fast enough. Because you could say, oh, these 10-digit numbers that I've created, there's 10 to the 10 of them, and that's loads. And it's like, great, I'm generating 400 a second. What are you going to do about that? I'll run out of them in, some reasonably short time frame. But that does sound like there are enough of them that even if all computers were using them literally all the time to produce, we wouldn't actually run out of them within potentially the life of the universe, or something reasonable.
Yeah, I suppose so. But then it's run out of them. But then you aren't. It's not like you're ticking through a list, right? So at any time another one's generated, it has this tiny probability of generating a clash, I guess.
Yeah. So it potentially still could happen. I realise that probability based things happen a very predictable amount of the time, but I suspect, given that it is small enough that you wouldn't realistically need to worry about it. And I suspect also people don't necessarily build anything that's system critical on the assumption that all of the UUIDs will be different, maybe.
Well, whether people do or whether people should, I'm not sure.
Yeah.
But, I mean, it's basically such a small likelihood that it's sort of ignorable, I guess.
Yeah. I mean, there are things built on much more fragile constructs, like, encryption algorithms that rely on not being able to factorize large numbers, but actually, given enough time, you can factorize anything, right? So
yeah, definitely.
It's just sort of sufficiently strong, sufficiently robust that we don't need to worry about it.
Yeah, and you're right. The order of the number that you need to create, it's like a million in one chance is all very unlikely, but in a city of 10 million people, suddenly that's looking like a bit of a, oh dear, So it's a bit like that. But the rate at which you need to generate them to have worry about this problem is not particularly close to what we're doing, I guess.
Yeah. So you were saying that given the UUID, you could in theory work out the MAC address of the computer that generated it. But you also mentioned hashing. So is it like an invertible function, or is it hashing in the sense that it's obscuring something?
Gosh, that's a good question. I don't know how to answer. Yeah,
because I guess if you're hashing, hash functions are these sort of one-way things that you can take some information, generate a hash from it, and then people can't necessarily know what your original information was, but they can say that you can use that to prove that you had the original information, because you can say I can regenerate the hash and get the same thing. So it's sort of a one-way function in that sense. But I mean, it's also possible for things to be partly one-way, right?
Yeah, I think the sort of secure hashing functions, but it was only some of the versions that use the hash function. You see, so your sort of standard version 1 just converts the MAC address into binary and then puts that straight into the thing. But,
easy enough, yeah.
It may not matter that who generated this thing. If you buy a product from that company and it has a UUID as its product code, and you're able to trace the product code back to that company, that's fine, right? That's not a problem.
Yeah.
So it depends, and you don't have to use that version of the UUID if you want to be kept secret.
And just for anyone who's confused, to check, MAC address stands for Media Access Control Address.
Yeah, I knew it's something weird. It's it's hard to keep that in your head because it doesn't seem to mean anything when you...
Yeah, to be clear, it's nothing to do with Apple computers. It's not only Apple computers have a MAC address.
Yes.
Yeah, that confused me at first because I had an Apple computer and it had a MAC address, and I was like, great, this must be an Apple thing. And then someone else was like, well, this is my MAC address. So I was like, oh, but you have a PC. But yeah, it's this sort of network interfacing identifier, I guess. But that's only 48 bits, right? So that's a much smaller space. Surely there's clashes in that, or is that enough for everyone in the world to have several computers each?
Yeah, so again, a quick hasty Wikipediaing tells me the 48-bit address space contains, of course, 2 to the 48 possible MAC addresses, which is over 281 trillion.
Yeah, that's plenty. We don't have that many computers.
No,
yet.
That's right. We'd need an awful lot of computers each to worry about that.
Yeah, I'm not quite there yet. So we are both on Twitter. I'm at Steckles.
And I'm at Peter Rowlett, and the podcast itself is at Maths Objects.
And both Peter and I blog at aperiodical.com, which is where you can also find more episodes of this podcast.
And if you have any thoughts, any suggestions, if you want to send us a UUID for whatever reason, then you can get in touch by email at objects@aperiodical.com.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.